morning. Today we discuss lecture number 14, which is durability 2. We discuss concrete corrosion, which is corrosion of the steel reinforcement in concrete. We discuss soffit attack and also durability of concrete in general. The cost of corrosion in infrastructure. Okay, every year people spend billions of dollars for maintenance of bridge. Okay, the most costly maintenance is the reinforcement. Okay, so hundreds of billion dollars spent to repair the corrosion of corroded bridge. Okay. So corrosion principles. It is electrochemical process. Okay. Here shows the steel reinforcement. Okay, we also have a concrete cover above the steel. Okay, so which is the barrier between the air and the steel reinforcement. Okay, so a healthy steel rebar has protective film on the surface. Okay, so this thin film protects the steel from further corrosion. For corrosion to happen, some part of the steel should be a damaged surface. So the surface, the thin film will be damaged. And that area will serve as a so-called anode. Okay. The chemical reaction involved with corrosion is called half-cell reaction. We have anode and we have cathode. Okay. In the anode area, steel, Fe, will lose 2 electrons and become Fe2+. This is oxidation process. The other part of the steel will serve as cathode. In the cathode area, water, oxygen, both of these two coming from the environment, okay, plus 2 electrons. So this electron coming from the anode area. Okay. In the anode area, electron is generated, and the electron will come from the anode to cathode area. So these 4 electrons will combine with water and oxygen. It will generate hydroxide ions. Okay. Corrosion products including rust. Okay, so Fe oxygen plus a certain number of water. Again, for corrosion to happen, we need anode. We also need a cathode. We also need a conductor. The conductor actually is the steel itself. The function of a conductor is for the electron, which is generated in the anode area, to go to the cathode area. Okay, so without the steel, without a conductor, the corrosion cannot happen. Okay, so electron will go from anode to cathode. Okay, from here to here. We also need electrolyte. Okay, electrolyte, the function of electrolyte is for the transportation of ions, such as hydroxide ions, okay, and also Fe2+. The ions need to go from anode to cathode in the case of Fe2+, or from cathode to anode in the case of hydroxide. Okay. Ions will combine together and rust will be formed. What is electrolyte? Electrolyte actually is the pore solution or the pore water in the concrete. So the concrete needs to be wet. Okay. Again, in the cathode area, we need both water and oxygen. Without any of these two, corrosion cannot occur. Okay. Okay. So here shows from the rebar, pure steel. Okay. In concrete, we need to have oxygen and also water. So we could have hydrogen product. There's different type of oxide and hydroxide of Fe. Okay, and we can see the volume expansion can increase up to more than 7 times. So that's the reason when we have rust, the expansion in volume will cause a nearby concrete to crack. Okay, so this is the cracks around steel reinforcement, and sometimes the concrete will also spall off. Okay. Again, corrosion will not occur if no water or no oxygen is available in concrete. Okay. This is important. Okay, so here shows reinforced concrete pier in seawater. Okay, so below the seawater, the corrosion, which is spalling of reinforcement, is not as bad as at water level. Above the water level, okay, the corrosion is also not as worse as about at water level. The reason for that is well below the water level, we have a lot of water, but not enough oxygen. Okay. Well above the water level, we have not enough water, although we have a lot of oxygen. Okay. Remember, we need both enough water and oxygen for corrosion to occur. So that's the reason at water level, we have both enough water and oxygen, and that's where the corrosion is the worst. Okay. So again, corrosion will not occur if no water or no oxygen is available. Right. The pH level and also the concentration of chloride has strong effect on corrosion of reinforcement. So basically, the more acidic the concrete, the lower the pH level, the more likely corrosion will occur. The reason for that is because higher pH level will help generate this protective thin film, the oxide film, on a steel surface. So that thin film will protect steel from further corrosion. Reduce the pH level, the thin film will be damaged, so corrosion will start. Chloride ions, which may come in from de-icing solution or seawater, will destroy this protective oxide film. So corrosion will be accelerated. Again, more chloride ions, more acid the concrete, more corrosion. And here shows how the pH level of concrete and how the concentration of chloride will affect the corrosion. Okay. Healthy concrete, the pH level is well above 13. Okay. You can see increase the pH level, corrosion will be less likely. Or we reduce chloride concentration, corrosion will be less likely. And based on that, we could have different zones. No corrosion zone, when we have high pH level and low chloride concentration. Okay, so based on that, we could have a general idea if a corrosion may happen in a certain condition. So this is a very basic introduction of how corrosion will occur. Okay. How to control corrosion? The most important thing is to control the permeability of concrete. Okay. Concrete with lower permeability, oxygen and water will have a harder time to penetrate into the concrete to do the damage. Okay. So reduce the permeability of concrete if possible. We can also increase the thickness of concrete cover. Okay. So that will also prolong the time for chloride ions to penetrate deep into the reinforcement. We could also do surface treatment. We could use epoxy coating to seal the concrete, so we can also reduce concrete permeability. Or we could use membrane penetrating sealers, again, to reduce the permeability of concrete. We could also treat the rebar we could use epoxy coated rebar, so kind of protection on the rebar. We can also use galvanized bars. So galvanization means we apply a thin layers of other type of metal, such as zinc or aluminum. Most likely will be zinc. So this thin layers of metal is applied on the surface of reinforcement, so the steel will be protected. The thin layers of zinc will be sacrificed. Okay, we also call that cathodic protection. Okay. We could also use non-metallic bars. Of course, if we use non-metallic bars, no corrosion will occur. Sometimes we could use admixtures, such as corrosion-inhibiting admixtures. Okay, so that admixtures will reduce the expansion of rust. So reduce the expansion, we reduce the cracking due to expansion. Cathodic protection, which means we treat all the steel as cathode by using some methods such as we attach a more reactive metals such as zinc, aluminum to the steel rebar. So these more reactive metals such as aluminum will serve as anode. Okay, so go back to the chemical reaction of corrosion. Okay, so in the anode area, the metal will lose electrons. If we attach a zinc, because zinc or aluminum is more reactive compared with steel, so these materials will serve as anode. So zinc or aluminum will lose electrons. So steel will be protected. Okay, so all the steel reinforcement right now become cathode, and that's why we call that cathodic protection. Okay, so that's another method for cathodic protection. We could use battery, for example, to provide extra electrons. So all the steel reinforcement will become cathode. Okay. Okay. So this is a very basic introduction of corrosion of reinforcement in concrete. Okay. Next, let's look at soft attack. Okay. When we discuss different type of cement, we know type 2 cement and type 5 cement are called moderate sulfate resistant cement and sulfate resistant cement. Okay. In these two types of cement, we reduce the amount of C3A because reduced amount of C3A will reduce the amount of potential etching die formation. Okay. So today we look in details of what is sulfate attack. So actually, sulfate attack is a blanket term covering different type of reaction between product of C3A hydration, okay, such as monosulfate aluminate, etching die. Sometimes CSH could also be affected, okay, depending on the type of sulfate ions. Okay. So as we can see from this picture, this is spalling due to sulfate attack. This is a concrete on the soil surface. Okay, from the soil, we could have some of the sulfate from the environment. So this sulfate may attack concrete, and we call that sulfate attack. So the sulfate ions could come in from groundwater, seawater, or industry runoff. Okay. Sulfate attack could be expressed as expansion and cracking due to formation of etching die. Okay. Or sometimes CSH may also lose its strength. For example, if the sulfate has magnesium in it. Okay. So there are many different types of sulfate attack. The first one is attack from sodium sulfate. Actually, it should be Na2SO4. Okay, so calcium hydroxide combined with sulfate ions, it will form gypsum. Okay, so this chemical reaction will cause 120% increase in solid volume. Okay, so in the concrete, we could have calcium hydroxide. It could combine with sulfate ion from the environment and form gypsum. This could cause cracking due to increase in solid volume. The second equation is classic sulfate attack. Okay, so AFM is the monosulfide aluminate, one of the potential hydration product of C3A, right? So combining with the gypsum, so this gypsum could come in from outside, from groundwater, from the soil. Combining with water, it will form ethylene. So the total solid volume will be increased, so 55% increase. So that may also cause concrete to crack. If the sulfate ions is in the form of magnesium sulfate, it will be more severe because magnesium sulfate will not only attack AFM and calcium hydroxide, like in the case of sodium sulfate, it will also attack CSH. And we know CSH is the major strength contributor to concrete. If CSH is degraded, the strength of concrete will be much lower. So if the magnesium sulfate is in a system, it will do more damage compared to sodium sulfate alone. Okay, so more severe situation. The third type of sulfate attack is DEF, or delayed ethylene dye formation. So I think we discussed DEF before in a lecture of curing. So if we increase the curing temperature, ethylene dye may be dissolved or destroyed into sulfate and aluminum ions. And these sulfate ions will go to other places. And when temperature drops, this sulfate will form ethylene dye again. And this will cause expansion in solid volume in some other places and may cause concrete to crack. Okay, so we call that delayed ethylene dye formation because the ethylene dye is dissolved due to high temperature and reformed when the temperature drops. We also have some other type of sulfate attack, such as somacite formation. Somacite is natural minerals. Okay, so this is a breakdown of CSH with sulfate together with carbonate ions. Okay, this is beyond the scope of this class, but just keep in mind when we talk about sulfate attack, it is not only related to sodium sulfate. There's many other type of sulfate attack. Sorry. So we discussed the mechanism of sulfate attack, how we can control the sulfate attack. Okay. For concrete, we can try to reduce the permeability of concrete because the sulfate ions will come in from the environment. Reduce permeability, the sulfate ions will have a harder time to get inside the concrete and do the damage. We could also try to use low C3A cement, okay, such as type 2 and type 5 cement, because it will fully converts the C3A into ethylene dye when concrete is still in fresh state. Remember, ethylene dye will do the damage after concrete hardens. When there's an ethylene dye formation after concrete hardens, that will cause damage. If you can fully convert C3A to ethylene dye before concrete hardens, that should be okay. However, keep in mind, not all the socket attack only attack etching guide or monosocket illuminate. Some of them also attack CSH, such as magnesium sulfate. If that's the case, just use low C3 cement is not enough. We could also use pozzolanic materials. One, it will reduce permeability because pozzolanic reaction will reduce permeability of concrete. Secondly, it will also transfer calcium hydroxide into CSH. Okay, so that will reduce, some of these attacks, such as the first one. So reduce transfer calcium hydroxide into CSH. So there's no the first equation. Right. Of course, if we can limit exposure to sulfate ions, that will be the best. Okay, so no sulfate from outside, no sulfate attack. All right, so this is just some of the hydration equation for CEE375, just reminding us what is chemical reaction for CEE375 and what is sulfate attack. Okay, so again, sulfate attack is formation of etching guide after concrete hardens. All right, so far we discussed freeze-thaw damage. We discussed ASR in last lecture, and in this lecture, we discussed corrosion of reinforcement and sulfate attack. So next, let's study durability in general. Okay. To check the potential of certain concrete or certain aggregate for some type of attack, we should do some tests. Okay. The biggest challenge is the time scale. So typically, if that's durability issues, it will take years or even decades for concrete to show these issues, okay, in the field. But how can we make sure the concrete will last decades before we make the concrete? In the laboratory, we make the concrete. We want to see if this concrete is immune to ASR. But how we can tell that in short time? Okay. Of course, we cannot wait years or decades to check the concrete is immune to certain type of attack. So we need some type of quick test. So here is an example. This is a real example. Okay. Years ago, we want to check if a certain type of Hawaii aggregate has a potential for ASR, silica reaction. Okay. ESTM has certain type of test. So this test is a so-called accelerated test. So basically, we use very high concentration of alkalis, okay, much higher than the typical pH level. Okay. We also increase the temperature of the concrete. Okay, so that will accelerate the chemical reaction. And because of that, we can see the result in 1 to 3 days. So at most in 2 weeks. So that result from one of these accelerated tests shows us one of our local aggregates positive, which means it will show ASR potential. So we cannot use this aggregate in the field. But however, in reality, we have used this type of aggregate for decades, and none of the real concrete has any ASR issues. Okay, so that means this ESTM standard test give us a false positive. Okay, so this is similar to see if we can hatch a chicken from egg. Okay, the real field test is to put the egg in 99.5 degrees Fahrenheit for 3 weeks, and then we can see if we can hatch a chicken or not. If we do accelerated test, very high temperature, in 5 minutes, no matter what, we always receive broiled egg. Okay, so how to avoid this false positive is a major issue we have in the lab. And from the discussion of all these physical and chemical attacks, probably you realize permeability is the key for durability. If we can reduce the permeability of the concrete, most likely will slow down or even prevent these attacks. So factors affecting permeability including water to cement ratio, okay, the size of the cracks. Okay. If the concrete has low water cement ratio, we have lower porosity. The pores will also be more unconnected, which means it has lower permeability. Higher water cement ratio, we have more pores, higher porosity, and the pores will also be more connected, which means we have higher permeability. Okay, the degree of hydration, which is defined as a percentage of cement hydrated, will also be a factor. Okay, but just use low water cement concrete, we cannot ensure a low permeability, which we'll discuss in a moment. For aggregate, it is relatively impermeable, for normal aggregate at least. But for some other type of aggregate, such as lightweight aggregate, which is very porous, it may become more permeable compared with cement paste. Okay. This curve shows us how the size of the crack affecting the serviceability of concrete. If the size of a crack is small enough, there's no leakage, sometimes the crack can also heal itself. Between 0.005 inch to 0.013 inch, we call that controllable leakage. Okay. Beyond that, we have visible leakage. If the size of crack is beyond 0.33 inch, so corrosion will be likely. Okay. For ACI building code, the limitation for the size of a crack is about 0.013 inch. So as we can see, increased size of crack, we have more problem. Because permeability is the key for durability of concrete, there's different ways to measure concrete permeability, including fluid or water permeability tests. We can measure the conductivity of the concrete and translate it into permeability. We can measure diffusion of ions of concrete, can measure porosity, air permeability, sorptivity method, or a so-called rapid chloride permeability test, or RCPT test. So this test is a very common used test to measure concrete permeability. Some other tests, such as pounding test, will also be available. Okay, so let's look at some of these measurements for concrete permeability. So this is a water permeability test. Okay, so in this test, we generate some type of cracks using load, for example, and then we can measure the permeability coefficient based on the famous Darcy's law. Okay, so the setup of the test is like this. This is concrete specimen. We apply a certain pressure gradient, delta H. Okay. The rate of fluid flow can be measured. Okay. The surface area can also be measured. Viscosity of the water is known. Okay. And also the thickness of the solid, the specimen, is also known. Okay. The only unknown here is the K, which is permeability coefficient. So based on Darcy's law, we can calculate the permeability coefficient of concrete. Okay. So in this test, we have correlation between the size of the crack and also the permeability coefficient based on the permeability test. We can see increase the size of a crack, we have higher permeability coefficient. And here shows the ACI limit around 0.015 inch, which is correspond to certain permeability coefficient. This is RCPT test, or rapid chloride permeability test. This is one of the ASTM standard tests. Okay, so in this test, we have two ends with a certain potential. The specimen is in the middle. We have epoxy coating at two ends, but at the other two ends, we have sodium chloride with 3% concentration and sodium hydroxide with 0.3 molar. Okay, so we measure the total charge in coulombs after 6 hours of potential applied, depending on how much charge is passed through the concrete. Okay, so we can have an idea of chloride permeability. This shows a typical concrete value based on water to cement ratio. Okay, and this shows what is the total charge passed after 6 hours. Okay, for some concrete, such as concrete impregnated with polymer or high-strength concrete with silica film or latex, the permeability could be very low compared with concrete with high water cement ratio. And here shows another test, which is how the volume fraction of coarse aggregate. As we know, for normal coarse aggregate, it is less permeable compared with typical cement paste. So if we increase the volume fraction of coarse aggregate, the concrete permeability will be lower. So as we can see from here, if we increase the volume of coarse aggregate, the RCPT value will be lower. Okay. Again, here just show you an example of how people check how the different mixed proportion affect concrete permeability. All right, so the next set of slides is very important. It shows us how water to cement ratio, the strength of concrete and permeability correlated with each other. Let's look at the water to cement ratio and the strength first. Okay, so here shows how the water cement ratio in XXL affect the strength. Okay, so this is concrete with different size of aggregate. MSA means maximum size of aggregate, 3/4 inch and 3/8 inch. As we can see from here, clearly when we increase the water to cement ratio, the strength will go down. Okay, so we know this already from early lectures. So water cement ratio is the #1 factor controlling the strength. The lower, the stronger the concrete. Okay. If we reduce the size of aggregate, okay, we increase the strength for the same water cement ratio. We discussed that before because by using smaller aggregate, we will reduce the stress concentration and stress gradient in the ITG zone. So the concrete will crack later, so the concrete will have higher strength. And here shows how the water cement ratio affect chloride permeability. Okay, so if we increase the water cement ratio, the permeability will somehow increase, but the correlation is not as strong as correlation between water cement ratio and strength. For example, for water cement ratio 0.45 and 0.52 is almost the same. Okay, so increased water cement ratio does not really increase or decrease permeability. Okay, and here shows how the strength and permeability correlated to each other. Okay, so here shows compressive strength in the y-axis, and here shows the total charge after 6 hours, which is a measurement of permeability. We can see there's no clear correlation between the strength and permeability. In other words, a stronger concrete does not necessarily means the permeability of concrete is also lower. So stronger concrete is not equal to more durable concrete. So this is very strong conclusion we can draw from here. So at least strength should not be used as the only indicator of durability. And why is that? Okay. And here shows how the size of aggregate affecting permeability coefficient. For the same water cement ratio, if we reduce the size of aggregate, we will reduce the permeability a lot. Okay, so same water to cement ratio. The reason for that is if we increase the size of aggregate, the ITZ will be weaker because the chance we have bleeding, which is water trapped behind or below the aggregate, will be higher. Also, the differential strain around ITZ will also be higher. So we have weaker ITZ. That will increase the permeability of concrete. Okay. So the method to reduce permeability is to optimize the mix design of concrete, not just reduce water cement ratio. Okay. We could also reduce the size of aggregate and other parameters. For example, we could use flash or slag or silica film to reduce the permeability. Actually, mineral mixture is very effective in reduce concrete permeability because pozzolanic reaction will increase the solid volume and reduce the permeability. So you do not have to use lower water cement ratio. You could use other things. Better curing, longer curing is also beneficial to reduce the permeability. Okay. If we can increase hydration degree, okay, if we can reduce the entrapped air, we can also reduce the permeability. If we can use surface coating, of course, permeability will be reduced. From the early slides, we see the smaller the size of the crack, the lower the permeability. So crack resistant design is also very important. We can use SRA, which is shrinkage reducing admixtures, and that will reduce the potential of shrinkage cracking. We could also use fibers. We'll discuss fiber reinforced concrete in future lectures. Fibers can reduce the size of the crack significantly. Okay, so that may also reduce concrete permeability. We could use other admixtures such as silica film or slag. So all these four concrete has the same water cement ratio, but the permeability is quite different. If we use latex, okay, so our concrete canoe team use a lot of latex in the concrete, so the permeability of concrete is very low. Okay. Right. Keep in mind, durable concrete is not equal to high strength concrete. Some high strength concrete is not very durable. High strength concrete actually is more susceptible to a certain type of shrinkage called autogeneous shrinkage. Okay. In future lectures, we'll discuss what is autogeneous shrinkage and why this type of shrinkage only occurs in high strength concrete. So if the concrete has high strength, but a lot of cracking due to autogeneous shrinkage, the permeability will be high and the concrete will not be very durable. Okay. Remember, deterioration is always associated with water ingress. If we can prevent water ingress, we basically reduce the potential for all kinds of physical and chemical attacks. And permeability is not directly related to water cement ratio. Strength is closely correlated with water cement ratio, but not permeability. Okay, so concrete durability is very complicated. Okay, so controlling strength by reduced water cement ratio is not very effective. So instead of strength, we also need to consider permeability. Strength is important because a stronger concrete will resist stress better. Okay, so can resist higher tensile stress for stronger concrete. But permeability is more important compared to strength because reduced permeability will basically reduce the potential for all type of physical and chemical attacks. The crack resistance criteria, or how we can increase the toughness of concrete, is also important. So after the concrete crack, due to different reasons, how the concrete can reduce the size of a crack is also very important. For example, we can use fibers to reduce the size of a crack, or use other methods to increase the toughness of the concrete. All right, so that's the end for the second lecture on durability. Okay, what is the role of water in durability? Remember, all type of physical and chemical attacks will involve with water. Okay, what is the mechanism and how we can reduce the frost damage, scaling damage, which is a special type of freeze-thaw damage, how to reduce alkali-silica reaction, how to reduce corrosion of reinforcement. Okay, so remember different type of chemical reaction for surface attack. Okay, and what is relationship between permeability and concrete durability? Remember, permeability is number one factor controlling durability of concrete. Okay, and that's the end.